the link to the next one. So leios.cardanoscaling.org gives you always the link for the next meeting. And of course, you're all invited. And actually, we can keep this on the side. Yeah. Now people are trickling in. It's nice. I wonder. It's working. Nice. Good. So we're ready to go. Good attendance. Everybody else needs to watch the intro. All right. Welcome, everybody. It's October 2025, and this is the monthly review meeting for Leios. I'm Sebastian. I'm your host today, lead architect on the project, and I'm joined by a wonderful bunch of people giving demos, updates, what's the latest, and progress on the Leios engineering progress. Our agenda today will be packed with demos. I have one about cryptography. We have one demo which is focusing more on networking, how traffic would interfere or not between Leios and Praus. We have a few slides on new results, simulation results, general feedback we got through the SIP. We have guests from TXPipe and Blink Labs commenting on their experience in wrapping their head around the SIP. And we'll have a bit more documentation and design documents we've been writing, but let's see if we get to that. We'll definitely get to a roadmap update so you know where we're at and what's next. And without further ado, I'm going to hand it over to Hamza, who's
Awesome.
going to kick off with a voting demo.
Thank you, Sebastian. So let me share my screen. Okay, so before diving into the demo, I would like to give some context. So actually, this demo is related to our milestone of showcasing 1K TPS. And more specifically, we have this issue here, issue 564, which is to showcase the voting and certification primitives. So with this demo, like we closed this issue. Before also showing the demo, I would like to show where the code lives, so everyone can run the demo by themselves if they wish. So I will share my VS Code. Where is VS Code? VS Code. Oh. Cannot see it. Okay, maybe I'll just share then the entire screen. Okay. Yeah, so can you see the VS Code?
Yes.
Okay, perfect. Yeah, so so this is Ouroboros Leios repo, and we have a crypto benchmark.rs folder that is dedicated to the cryptographic part, so the voting and the aggregation that we'll discuss today. And in this folder, there is a subfolder demo that contains some scripts that call the cryptographic layer and also front end that will run just now. So let me launch front end. And with that, I will move to the UI. Okay. Yes. So basically, I'm running this demo on my machine, which is an Apple M1 CPU with 8 cores and 8 GB of RAM. So here, first we see the set of SPOs represented by these circles. And if we hover over one circle, we can see the pool ID and the stake. So here we have 499 SPOs with a total stake slightly above 1 million ADA. So all these pools are eligible to be selected for committee selection. Oops, okay. Yeah, so now we are at the beginning of an epoch, so we will select the committee of voters. The committee here is composed of 100 seats. And there are actually two types of seats, as you see with the colors. There are the green seats and the blue seats. The green seats correspond to the persistent seats. These seats are filled with pools for the whole epoch. So these pools, they don't change for the whole epoch, and they were selected via fait accompli algorithm. And the pool that got a seat has voting power for all the EBs of that epoch. And these are typically pools with high stake. For instance, we can see that the first one has 21,000 ADA, the second one 19,000 ADA, etc. And to keep the process fair and open also to pools with lower stake, we have the non-persistent seats that are represented here. But at this point of time, they are empty because they rotate for every EB. So as now we don't have an EB, they are still empty. This committee selection took 90 milliseconds on my machine. So now let's start the election for a given EB. This is the election ID, and this is the hash, the hash of the EB that our pools will vote on. So let's move to the voting. So first, let's see the votes coming from the persistent seats. So we had 76 persistent seats, so persistent voters. 57 of them decided to vote. As you see, the first two, for instance, didn't vote, while after that, these pools decided, or these seats decided to vote. So the vote is represented by this rectangle here. So let's look at what is the vote. So the vote contains the seat ID. And this is enough to uniquely identify the voter, because the voter here, the persistent voter, is the same throughout the epoch. So we have a clear mapping between the seats and the identity of the voters. And it contains a BLS signature about on the EB hash. And the size of this vote is 134 bytes, which we'll see that these are the smaller votes. Now let's move to the votes for the non-persistent seats. So now you see the non-persistent seats were filled with some pools, and the vote coming from a non-persistent seat is represented by a larger rectangle because it's actually bigger. It's 247 bytes. And the reason is that it contains the pool ID, because remember that these seats, they are filled for every EB by a new pool. So we need to, the vote needs to contain the pool ID and also an eligibility proof. The voter here, the non-persistent voter, needs to prove that they were eligible to vote for that EB. So that's different with the vote from a persistent seat, where they are eligible by default. So they don't need the persistent voters. They don't need to provide an eligibility proof. And this is actually our first key optimization here, is by introducing the persistent seats, we have a smaller votes for the persistent seats, while we still have larger votes for the non-persistent ones. Roughly in total, we have around, as I mentioned in the committee selection, we have 76 persistent seeds. We have 24 non-persistent seeds. This voting took 282 milliseconds to generate all the votes on my machine. But of course, in a real system, this will be decentralized. And in average, a vote takes a bit less than 4 milliseconds. Okay, so now let's move to the aggregation of those votes. This is done by the block producer. So the block producer receives all the votes and needs to generate a certificate that contains all these votes. So the votes are large, even with this optimization of persistent seeds. The total size of the votes is 12 kilobyte, which is above the limit of Browse block. But using BLS aggregation, we can compress it to a smaller certificate that you see here is 5 kilobyte. This certificate contains the BLS, the aggregated BLS signature of all of the signatures of all the voters. And yeah, and I forgot also to mention that for the block producer to be able to generate the certificate, it needs to have collected votes that reach the threshold, the quorum. The threshold here is 75% for Leios. Yeah, and the aggregation time took 75 milliseconds on my machine. And this certificate now was added on-chain, so anyone can verify it. So we can move to the verification. We can do it by ourselves here, and we see that it was successful. So verifying the certificate proves two things. It proves that this BLS signature was successfully or cryptographically verified with respect to the public keys of all the voters. And it also proves that the quorum of 75% was reached. Yeah, so that's all for the demo. The key message here is that we introduced for the Leios voting two key optimizations: the persistent voters, which allows us to reduce the size of the vote, and the BLS aggregation that further compresses the votes to fit into one block size. Yeah, that's all, and I'm happy to take any questions or feedback.
Thank you. We have a quick one maybe from Nick.
Yeah, it should be quick. Thanks. So thanks for the demo. I noticed at the top you said you had an 8-core machine. And I was wondering, for the millisecond times you listed, were those using all 8 cores? Like, does it take 75 milliseconds to check a cert if you're using 8 cores to check the cert, or is it just using 1 core? Do you know?
If I'm not, there is no parallelization, but I don't know if Brian is with us. Maybe he can.
I don't think there is any parallelization, but single core clock times does influence it. On my Ryzen, for example, it was about half of these milliseconds here, which is 4 gigahertz, maybe compared to your laptop, 2 gigahertz, whatever. Sounds reasonable. And one thing to note, it's really about quality here, not really about the exact quantities, because these measurements here are also not exactly on the thing which will end up in the node. There is some inter-process calls here involved in the demo. So another few more benchmark representation, a better representation will be kept around throughout. Yeah, this is more of a visualization and gives us a quality understanding of what's going on.
Thanks.
Thanks for giving us a demo, Hamza. And I will just right away hand it over to Nick. I think you can take the screen without going to mine.
Okay.
What's your next?
I forget where the play button is. Is it here?
Yes, it's visible.
Okay, great, thanks. My demo is not as pretty. That was a very pretty demo, but none of us allocated to this work this month were front-end engineers, so to speak. So bear with me, please. All right, so bottom left, issue 1701 in the Ouroboros consensus repository. You can see the work as we sketched it. Off the top of my head, I think it's issue 544 in the Ouroboros Leios repository. But the big idea is, actually, how do you spell that? Sorry. The big idea is we wanted to get some code running that's actually moving bytes around, and to measure its effect on Prouse, right? So one of the fundamental aspects of Leios is that it is an overlay protocol. It takes Prouse for granted. And something that took me a long time to realize is that means that it's assuming the Prouse performance is not affected by the Leios work. When I say it's assuming, I mean like the Ouroboros Leios paper, right, is assuming that the Leios traffic doesn't slow down the Prouse traffic. But in our node, especially with the single GHC heap being used for both, that's not, we can't take that for granted. We're going to have to actually do some engineering to achieve that. So this demo represents or shows our first steps towards measuring that. And once we can measure it, then we can start iterating on it to try to actually make it true. So I've got some visuals here that I'll talk through briefly. But I should clarify first. I'll start with the diagram in the middle, right? So for this demo, we just have a very simple setup. We have a 3-node network. The middle node is what you should think of as the node. It's a node that we have patched to run the 2 mini protocols for Leios. They're not running the full Leios algorithm, right? They're only running the parts that are necessary for moving EBs around. So there's no votes, there's no recovering when you're behind. It's just if the mocked upstream peer offers an EB, then the node 0 will fetch it. So we're just handling the EB parts of the mini protocols because that should be the intensive aspect. So it should be able to demonstrate the effect we're trying to demonstrate. Okay. In particular, it's not doing voting, and moreover, it's not. None of these EBs are being included on the Prouse chain. So we don't actually need real transactions. So for us, for this demo, transactions are just random byte strings. So they have a weight, right, a size, they take time to move around, and they have a hash. And that's what we need in order to write the logic. Someday, we'll also add the voting and the validation, in which case the TXs will need to be real. But for now, we're in the nice position where we can just generate whatever shape of Leios data we want. And I'll get to that on the next slide. Okay, so the mocked upstream peer is offering Leios data, and the node 0 is pulling it. And then we have a mocked downstream peer, which is also requesting the Leios data from node 0. So node 0 is both receiving the Leios data and forwarding it, just like a relay node would in a real network, right? Simultaneously to that, the mocked upstream peer is also serving Prouse blocks. And node 0 is receiving those Prouse blocks, and it's relaying those Prouse blocks to the mocked downstream peer. So we talk about it in terms of the Leios load or the Leios traffic and the Prouse load of the Prouse traffic simultaneously. That's the interesting part of this experiment. So at the bottom, you can see the primary measurement of this experiment, which is the latency of some Prouse blocks. In the first area, I don't know if you can see my cursor, but in the first outcome, you can see the latency of each Prouse block was around 600 milliseconds. And in the second run, that latency was around 3 seconds, right? So that's much worse. What's the difference between the 2 runs? In the first run, there was no Leios traffic. We just set them up and let them run, and the Prouse stuff happened. In the second run, it was the same Prouse traffic, and we also had some simulated Leios traffic. Or I shouldn't say simulated. We had some Leios traffic with this mocked Leios data. And just the presence of the Leios traffic caused a 3-second delay in the Prouse diffusion times, which is unacceptable, right? However, it's not surprising because this node 0, we took a month to add all the necessary Leios logic to it, right? Like I wouldn't have predicted that it would be efficient. And as we did that, we learned a lot. One of the things we learned is there are quite a few knobs that weren't even like on our radar when we're writing the SIP, but they're going to have to be tuned. And I don't know how to tune them. A month wasn't a time. We didn't have a test harness until the end of the month, right? So now that we have a harness, we can tune those numbers. So this 3-second delay it's a scary number, but it makes sense because this isn't, a node that we're going to suggest putting on mainnet. This is the first Haskell node that's ever ran any Leios, right? So it's got performance bugs probably. But now that we have a good harness in place, now we can dive in, try to fix those performance bugs. And our goal will be to run the same harness and show that the latencies don't increase. But that wasn't our target for this month. Our target was to have what you're seeing here, which is a demonstration that Leios can disrupt Prouse. And it's going to take some work in order for the Leios to not disrupt Prouse. So I can talk through a little bit more about what you're actually seeing. But if you have any urgent questions, feel free to interrupt. So that is the diagram and the little table at the bottom. On the right is the schema that we're using to store the Leios data. So for this exercise, it seemed appealing to try out using SQLite for our storage. We have other options, right? The node has a custom file system-based storage for Prouse data. The UTXOHD node has the LSM tree backend. Those all have requirements that make sense for motivating those backend storage mechanisms. For the Leios data, none of those requirements were the same. Like it had a different set of requirements that were generally simpler, less or weaker requirements, right? Easier to satisfy. So using something that's simpler and better, a very mature piece of software as the backend seemed appealing. So we're trying that out in this demo. So in particular, the main table is the EBTXs. The EB points table is just sort of for database normalization. If you remember your DNF forms, I'm not going to make a claim about a specific degree of normalization, but basically the hash of an EB is 32 bytes, and I don't want to repeat those 32 bytes for every single transaction because there can be up to about 14,000 per EB. So the normalization here is really just motivated by not wanting to waste space. So the top table is just for giving EBs compact names. The second table does all the work. It stores for each EB and for each index within an EB, the hash of the transaction at that position inside of the EB's closure or in the EB body even, the size of that transaction. Right? And then if we have it, right, it's a nullable column. If we have it, then we also store the transaction data there, but we might not have it yet. So at the end of this demo, the database for the node 0 and for the mock downstream both have a full EBTXs. Right? At the start of the demo, the mock upstream peer has a full EBTXs table. And by the end of it, the other nodes have pulled that Leios data through the network and have stored it in their database. Okay. So just briefly, this is my last slide, and it has a link. So important thing for you to remember is like if you want to know more about what you're actually seeing a summary of, you can go look at this README, and it says a lot more than what I'm about to say in more detail. And it also tells you how to execute it if you can bother checking out the branch and building from source, etc. Okay, so one of the first steps of the demo, as you'll see if you go look at that README, is to just generate some Leios data, right? There could be all sorts of different kinds of Leios data. For this demo, right, for these specific latency numbers, the way I achieved these numbers was I built a pretty intensive burst of Leios traffic. On the left, I've specified 10 different EBs. And when I say specify, these aren't the EBs themselves. These are just a recipe, right? So it says what slot the EB's in. And then for each EB, it also says it has this many transactions. And for each transaction, it gives a byte size. So 16,384 is 2 to the 14th. That is the current limit of a transaction on mainnet. So for this demo, I used beefy transactions And remember, they're not being validated or anything here. They're just byte strings for this demo. So it's totally up to us how many transactions we have and what size. But my goal with this data set for this demo was to have EBs that were 12.5 megabytes. That's as big as they can be, but do it in the fewest transactions. I think this is about 763 or something like that transactions. All of them are maximized except one of them just fills in the last missing gap. So we have 10 of those. The slot numbers are meaningless, right? Because in the Leios protocol, if a node learns about an EB, it should acquire that EB, assuming it has the right proofs for eligibility and whatnot. But for this demo, we're just trusting that the EBs are all valid, which is fine for the demo's purposes. So if it learns about a new EB, it's going to try to fetch it. The slots only tell us how it'll prioritize one EB over the other, but otherwise they don't mean anything. So in particular for this burst, right, I just did the simplest possible way to demonstrate that browse can be disrupted in a, roughly implemented Leios implementation. For this burst, all of these EBs are being served simultaneously. They're being announced all at once. So on the right is the schedule of when the mocked upstream peer will send the first messages in the Leios mini protocols, right? So see my cursor maybe in the bottom left, the second level of bullets here. The first message it ever sends is it offers an EB to the node under test, and then it'll later offer the transactions in that EB to the node under test. And this little schedule on the right just says when each of those happened. So the 182.9, that's interpreted as a slot number, right? So it is 9/10 of the way through the slot 182. That's when the mocked upstream peer announces this data. And the node under test will respond by fetching it. And now it's doing work. And that work, as we showed above, for this roughly implemented node, disrupts the browse times. So the key thing about this data is you can shape it however you like. We don't need it for this demo, but the syntax here can also represent that some EBs share transactions with other EBs, which will be interesting for later. But for now, we don't need it for this. This is sort of the worst case, right? Where every EB doesn't share anything else with anybody else, and so you have to download it all. The last thing I want to emphasize, oh, go ahead, yeah.
Yeah, can you show us this perfect storm here, maybe within 5 minutes maximum, so we have other stuff too?
Okay, yeah, sorry. All right, so we can create the data and we can repeat it. We can run the test multiple times. It'll serve the same data at the same time, so we can get some iterations. All right, so this is all the details that came out of one run. You can see on the left there was no Leios traffic. The last few bytes were, or last few blocks, browse blocks, or 600 milliseconds latency. And on the right, you can see that the Leios traffic interfered, and we added time to those blocks. I can't tell you why it interfered because we just got it up and running. Now we can measure it and see it's bad. So over the next month, we'll be iterating to drill down, try to optimize our Leios implementation such that these numbers get smaller and smaller. And if we can't get them down to the same latency, then that's a demonstration that we have to overcome this challenge of Leios disrupting browse. All right, last slide. The November plans are what I just said. On the bottom right, you can see just kind of the amount of code we had to write in order to get this demo going. And then I'm out of time, so I'll just mention we had to solve a question that we didn't anticipate needing to solve. That's what the top is. It's a minor question, but the demo just does something straightforward, but it might be naive in the end. We'll have to see. All right, that's it for me. Thanks. Any questions?
Is there anything? No. All right, so we all go and verify your results using our machines.
Yeah, let me know.
And package it up in Docker containers, see it in antithesis simulations, right? Or just have a next run of it. Anything goes. I think everybody feels nerd sniped, hopefully. And I'll take it, I think it's on my screen again, yeah. I'll take it forward to now we talk about the SIP itself. We want to briefly summarize latest feedback, some new results. Will? You want to take it?
Yep. Thank you, Sebastian. All right. Yeah, with respect to the Leios CIP, I'd say the overall sentiment remains very positive, even though we've received some valuable feedback that we've taken very seriously. In essence, those are 3 points that were raised, and each of which we've analyzed carefully. So the first one were basically questions around our proposal to simplify layers, or which we call linear layers. Can you go back the slide? Sorry, I'm just going to stay there for a second. And yeah, basically, it's a whole question around whether if our approach is basically the right one, or if we should go with something that is closer to what has been described in the research paper. And the second part, second bullet point here is concerns about the performance and how the protocol behaves under heavy load, whether it degrades. And the last one is around potential front-running opportunities that were introduced. And we took all of this feedback very seriously, as I said, and went back to provide some more evidence. And that's basically what has been linked here in the pull requests, if people want to dive deeper. But yeah, so that process actually helped us discover a bug in the simulation, so which once fixed actually improved our throughput numbers, which was great. And yeah, let's take a deeper look at some of these, what these PRs actually did. So for the discussion around the rationale, we actually opened a public thread on the CIP pull request to keep the discussion open and transparent. We actually think this is probably the best way to have an open discussion and give everyone the same equal opportunity to voice concerns and support. So feel free, if you have an opinion, read it and let us know what you think. And then moving on to the next slide, performance. So this is, since Brian is currently on holiday, I'll summarize his excellent work that he did together with Simon. Basically, they've updated the REST simulation and run the latest simulations again for these results. So what you can see here is the throughput behavior of layers as demand increases. So to put it in Brian's words, a well-behaved protocol's throughput should plateau once its capacity is reached, and performance should not degrade further when demand exceeds capacity. So given the protocol parameters that we specified in the CIP, the capacity of linear layers is currently around 300 transaction kilobytes per second, and that translates to around 200 TPS, considering 1500 byte transactions. So let's take a closer look here at the graph. So we see at the x-axis it defines the load denominated in transaction kilobytes per second, and the y-axis is our throughput or capacity. And we see how it nicely matches up to our upper limit of the 300 transaction kilobytes, and then levels off and flattens. And at these higher levels of demand or load, clients would basically experience back pressure, and because we're basically exceeding the capacity of the protocol. But what's key here is that it doesn't degrade. It doesn't like fall off a cliff or whatever. And in other words, the clients would basically experience maybe a larger delay when they try to submit a transaction to get into the mempool of a node, just like it is in parse today. I should also mention that these minor variations, like that you can see here, these fluctuations, they originate from the randomness in block production, and also likely due to our shorter window of simulating the protocol. So these would average out over time. The whole simulation is here a 20-minute simulation. And then on the next slide, we're looking at delivery times. So the time from the transaction submission to ledger inclusion in form of these candles, where the circle represents the median and the lower tick the 10th and the upper tick the 90th percentile. And we actually get a very similar picture like on the previous slide. So when demand is below 300 transaction kilobytes, the inclusion time for transactions stays stable. And once we cross the capacity limit here, we see longer waiting times which in our simulation are a bit exaggerated because we have an unbound mempool size. So we don't actually have back pressure right now simulated. So in reality, a real implementation would apply back pressure such so that delivery times would remain constant, and we would basically task the client to handle a resubmission of their transactions if they receive back pressure. And on the next slide, moving on, we have another perspective on delivery times. This time it's relative to parse. So here again, the x-axis shows the load on the system, while the y-axis now shows the additional time a transaction takes to reach the ledger under Leios. So, and at very low demand, the Leios imposes only a small delay because many transactions are included in RBs. And then as we push up, increase the load, the demand, then we see transactions being included in EBs up to the capacity limit, where then nearly all transactions appear in EBs. And their delay imposed by EBs does not vary with load, so that's key. So we see a relatively constant 40-second extra latency due to Leios.
Maybe a quick thing to point out, kind of as this is in comparison to Praos, right? We see the load demand in the bottom, and Praos can handle theoretically 4.5 transaction kilobytes. So it's really the first couple points here. This is what you would expect maximum, like for Praos, and we didn't really look at very small, low delays, but it's quickly actually already in the Leios domain of what can be handled. Just remember, right? 5 transaction kilobytes is really in the first bit on this 100. It's on the metric here.
Yeah, thanks for pointing that out. So again, like this jitter in the points, that is again because of the randomness in block production and our shorter time frame of simulating. And then we have one more graph, if I'm mistaken. On the next slide, we're showing the CPU and network usage per transaction. And what we see here is basically a healthy protocol, which does not consume more resources per transaction as load increases. So on the left side, it's a bit small, but you can see CPU usage, and on the right-hand side, the network usage. So in other words, the linear Leios CPU and network usage per transaction drops and levels off with increasing demand, staying well within the capabilities of a 4-core machine. Yeah, I think, Nick, you have your hand up.
Yeah, on the right, I think, so back when I first looked at some of the comments the SIP received, I think it sounded like some of the concerns were about the voting was happening even when there was no load. So in my mind, I was expecting to see like a baseline networking cost on the right, but maybe it's just so small because the y-axis is in megabytes. So like maybe the voting overhead isn't visible on the right, but it sounded to me like the voting overhead is what was the concern about, you're always paying that even if there isn't much traffic. But I'm just not seeing it. But maybe that's because the Y scale is off. I don't know. Do you have any, off the top of your head, do you know what the voting network usage was?
I don't know.
Existing figures in the SIP would actually address quite well to classify which egress is due to which kind of communication. And in this graph in particular, you will not see what part of contribution the voting has. As you say, especially when there is not much traffic, right? This is really not many of these simulations are done under not much traffic. It's only the first couple of points here. So the SIP would go into more detail here. And what we can see here on the right-hand side is that the per transaction cost, which is shown here, is actually sometimes bigger here again, right? Because there's lots and lots of transaction submissioning happening here because there is no non-back pressure simulated here. So the simulation has unlimited mempools in this version we used here. In the meantime, we released version 1.4, which has this bounded mempool. So they would only accept that much transactions in a mempool and not try to distribute it even. So we would see much more well-behaved on the overcapacity situations we see on the bottom right here. So it's really now up to let's do all the same data again with the 140 simulation, which will take only like 2 weeks of compute time. But that is interesting.
Mm-hmm.
You have a question also?
Yeah. Any questions? Otherwise, I have one more point.
Yeah, go ahead. It's not about Hydra here.
Sure. So yeah, the last part or the last thing that we've received was concern around front running, and yeah, we've acknowledged that this issue is existing, and while it isn't specific to this particular version of Leios that we propose, it would similarly apply to other variants, including the one that was specified in the research paper. We are taking it seriously, and I want to say the likelihood of front running appears to be proportional to the throughput. And we've been aware of this concern for some time because of the community member pointing it out, and we've encouraged that person to open a thread on the CIP. Since that hasn't happened yet, we plan to initiate our own dedicated thread ourselves and explore potential mitigations. And we'll share an update on that next month. And yeah, with that, thank you for listening, and I'll hand it back to you, Sebastian.
No, I hand it back to Pedro, who has been also concerning himself with the SIP from TXPipe.
Hi, how you doing? Okay, well, I will talk about how the first approach of implementing the Leios primitives at Palace, which is TXPipe's toolkit for building for working with Cardano. So I will share my screen. Okay, do you see the screen?
Starting, yes.
Okay, so this is the Palace repo. Just as a brief introduction, it is organized as a series of crates of packages. They are described here below, and in particular, Palace primitives crate includes all the primitives of each era of Cardano. You can see it here. It's organized in some folders, and the new one here we're seeing my fork, and there's one with for Leios, and this in turn inside the Palace Traverse crate, they are all intertwined, so you have a uniform way to access them. And for Leios, inside each folder, you can find the model source file that includes all the primitives. Well, this is just a quick glance, since Leios it would not be an era, but I'm not sure if it will be a new era, but I put it in as it put such. And it doesn't have many things because it inherits many things from Conway, and so we have the new block definition with the EV certificate here at the bottom as an optional field. The EV announcement. I think I got this. Yeah. Okay. In the header, we have the optional EV announcement field and the header body, and we have the other structures. Yeah.
I think we're only seeing your GitHub, the root of the repo.
Oh, why is that? Well, I will
maybe just reshare. Yeah.
Yeah, I will do it.
Chris is already looking for, where is the definition?
Yeah, I'm sorry.
I want to see it in Rust. I have it in Go. Yeah, now it starts again. Yeah, now we see some Rust code. Yeah.
I'm not sure. I feel that there's some broadcast problem. Is it moving? I'm scrolling right now.
No, it's only a snapshot of your first take. So we see a transaction reference.
Oh, okay. So it's not quite moving. Well, okay. So well,
Can you give me a link?
Yes. So this is a palace. I can share it right now.
Just drop a link in the chat.
Yeah. So there. So as I said, so I will stop sharing for a while. So as I said, the model file, source file in each era has all the primitives respective to that era, and you can find there those primitives, and in the so that's the let me check. So they are the primitives there that I'm not quite interacting with those. And if you go to the root, to the palace, to the root, yeah, there in Palace network, the first one, yeah, you have the mini protocols at source, yeah, and you can find there Leios notify with the messages and all the infrastructure. It's kind of similar to the chain sync and all this stuff. So we are looking at, these are the messages of at this point, if you check this out, at this point, the structures, the structs in network are decoupled from the ones from primitives, because we're in a process of making this a bit more generic. So we are trying not to force any dependency between primitives and network, the network crate. And I have a binary demo that it's in the folders in the root in examples. Yes, and then you Leios. That's it. So you go, if you download the repo and you step on, you don't have to move to switch folders. If you stand on the Leios fetch demo, yes, but you don't need to move. So just this is a Rust introduction. So you download the repo, you just do cargo build, and it will do everything to run. And the binary, if I will try to share once again. If I'm
Yeah, go ahead.
I will try to do it. I'm not sure what's happening. Well, so I want to share in my entire screen. Share. Do you see two terminals?
Yes.
Yes.
And it's moving.
It's moving.
Mm-hmm.
So this is the server, and we have the client here, and they are interacting. So this is with all the tracing for the communication, and you can see the raw data here, all keywords, and if I modify the client, I will hack this right now. So I will avoid asking for waiting for the response for the server, and I will try to build this. Okay, it's quick. So I run the server, I run the client.
Yeah, it's, I think the stream stopped again.
Stop again. I want to show this, so I will try again.
Yeah, go ahead.
So
We
because
have a few more
I'm on
minutes.
fire. So I want to, because the build one was successful in the screen, yeah. So I will, perhaps you can, at least you can see the output.
It's moving, yeah.
Yeah, are you looking at it? Are you
Yeah.
looking at both terminals? So we have a failure here intended, because so the server says it was disconnected, and the error here was that the client tried to send done, the message done, and the agency was not theirs. So
yeah, so it stopped again, but I think we see that the protocol is followed, right? That's what you want to say.
Yeah. So it's taking care of agencies and all the stuff. So this is made between in two terminals, but when I get acquainted with this new version of your demo, of the Haskell demo, I will try to connect this with Dot. So well, that's all I had to say. Thank you very much.
Thank you. Connect all the things, right? Chris, you also shared just the Go link, right? So everybody is really looking forward to just get the stuff connected.
Yes, we've got the protocol part implemented. We haven't hooked it up to a node just yet because we've been spending a little more time focusing on the node to client part and the changes on how that might operate. So I did put in a very tiny PR here to the Leios SIP into the Cardano scaling repo for us to start discussing what changes should be there. And the next thing that I'm going to add to it is essentially like what the node to client block might look like, that inline merged block that's actually described in the analysis. And I have the link for that too right here, so I can dump it real fast for everybody. And the analysis mentions, you know, the possibility of having a merged block that's essentially served over node to client, meaning we inline the transactions from the EB into just the transaction body, so that it minimizes what has to change in clients. Interestingly enough, I've been talking with Aurora on my team about it, and we were talking about how writing it up, and she completely disagreed with how I was wanting to do it and some other things. So it's a pretty lively debate, and I'm trying to now move that. I was like, that's great. Let's start it in front of everyone and continue there. So I'm going to put in a example shape of what my initial interpretation of this is to kind of go into the SIP. And the main thing is the words that I put into the actual change of the SIP is essentially that we need to take into account that there needs to be some standard on how we might change the node to client, especially for the chain sync blocks, because that's used so heavily by clients in the ecosystem. And I want to make sure that we're kind of taking that into account in the design changes that we're making, because it's going to be such a big change downstream. Mm-hmm. And that's one of the goals of, you know, the linear Leios is to reduce those downstream changes. So I want to make sure that it's something that, you know, we've put in front of everybody so we can have time to discuss.
Awesome. Really, yeah. Client interface is something we deliberately not touched much in the SIP on, right? But it's a very important piece covered by the impact analysis as we showed last month. And yeah, so it goes both ways, right? All of this kind of proposing and then being corrected sometimes even, or just being expanded on. So thanks for the contributions to everyone here. And this is basically a good segue. I'll try to be very quick. Actually, I will not be able to talk about it, but we're writing more documents, right? So not only the impact analysis, this was more of a stepping stone to a proper full-fledged technical design, which now takes all the understanding we had from the SIP now into much more concrete scope of a node level design. This has been progressed. It's basically, it's not complete, right? Because it will be a living document, but the whole shape of it, the whole context of it is kind of present now. So you would find what's our general approach on like tackling all of these uncertainties still assumptions or things to validate early? What is the overall implementation plan? What is maybe a bit more of a detailed discussion? What is the interaction between Leios and Peros, for example? How does it interact with Mithral maybe? And now here again, the client interfaces might be the only touch point here, right? And so on. So we'll see. And of course, all through all the layers, all the architecture, what will need to change? No, so far we don't see that there is like a pivotal change in architecture needed, but rather enhancing more of the same. This picture doesn't show it very well, but yeah, it's a bit maybe hard to see. This is a C4 document component diagram, but you see this is the relay node, the upper parts, the white ones. So this is the live parts, and this purple ones is the parts which are likely going to be needed to kind of do this more communication, but it's still kind of the same directions, more of the same. So we're kind of building this understanding and coding this into this technical design document before it gets kind of to benefit everyone who is also building on this. So while we have working on this, the SIP was really a proposal to initial acceptance to see what everyone thinks about, gather feedback. It's a protocol level specification. Now we really gathering the views from different viewpoints. Everybody has their own code base in mind. We saw the Rust one, the Go one. So everybody figures out what does it mean for my tool, for my infrastructure. So impact from all different viewpoints is going to be gathered into an analysis. When we are building a concrete Leios node in all of these emerging but also existing reference implementations, we're going to need to solve concrete problems, and design decisions need to be made. This is to be written up. This is what we call this technical design document. But ultimately, we need to also do work for those who come after, which is amend the SIP where needed, contribute to the blueprints where it fits. So make sure that we have a common understanding on implementation, independent understanding of what is Cardano. I can't go into the detail of the transaction cache, but it was something which we didn't really discuss much on the SIP, but only by trying to implement it now, prototyping on it, we have a much better understanding on the details needed for sizing it, but might be even kind of contributed back to the protocol definition. So let's assume this was a 1 hour meeting, right? So we have at least 2 more minutes to kind of have a look at the roadmap. Just as you saw in the demos, let me just maybe, can I just collapse this? This is possible somehow, new browser, sorry. Yeah. Oh yeah, so it should be a bit bigger. We saw the progress, the feedback, incorporation, discussion on the SIP is still in progress and still ongoing. This is desired, this is intended. Last month, we saw the impact analysis being completed. The technical design document is also in a very good shape, kind of has been put to a state which everybody can be contributing to it now. And it is going to be a thing we see throughout too, but we'll probably want to wrap this up too. The demos we saw was the voting and simplification primitives, as well as the interaction between Leios and browse traffic, which was the first measurement and first prototype, which is basically the first step of more network prototyping, which is one of the biggest uncertainties we need to kind of work on and validate early. On the crypto side, what we saw, there is also next steps due. So we really want to kind of refine the APIs to the node implementation, the integration points used in the Haskell and the Rust node and a Go node, and like just make the primitives, the BDS signatures needed for voting, signing, verification, aggregation available, along with a benchmark to really see this is kind of tightly narrowed down before and future audit will need to be happening on the crypto. That's why it's important to do that right away. More prototyping, more benchmarking is to be expected. And we also refined the work on threat modeling, the blueprint contributions, but most importantly, that's the next steps on conformance testing. How do we put the formal specification to good use? adapting the trace verifier so it can work on traces emitted by nodes too, which will give us certainty or a good handle on consistency across 2 dimensions. One is as we mature from a prototype into more and more mature implementations, but also across the various diverse implementations in multiple languages and so on. So that's basically it. So you can expect more demos, more exciting things. End of November is the next instance. We don't have much. We're running out of time. We're over time on questions. Maybe a quick call to action. The SIP pull request 1078 on the Cardano Foundation SIPs repo is the biggest one we want to have your feedback on. At any point, feel free to raise issues, start PRs, start discussions in that or in the Robust Leios repo you see linked here. And that's about it for today. Thanks, everyone, and have a wonderful Halloween. Just stopping the stream. That happened.